Hello. In this video, we are going to use our knowledge of exponential functions and their properties to solve an interesting application question about the half-life of an exponential decay function. More specifically, we're going to use the radioactive decay of carbon isotopes to estimate how old a particular fossil is using an exponential decay function. In the previous video, we talked about the doubling time of an exponential growth function, and here we have the corresponding notion of a half-time, the opposite of doubling, a half-time for an exponential decay function. For an exponential decay function of this form, the half-life is the change in x, the change in the input required to make the output half as big. And this value depends on only the constants a and b that are in the function, and not the actual value of the function or the input x. It's inherent to the function itself. It doesn't matter where you are along the curve. The change in x required to make the output half as big is going to be the same constant value. And before we jump in and do this specific example, I think it might be worth writing here a little bit about where that's coming from. Let's look at the initial value of this function. When I take this exponential decay function, and by decay I'm assuming now that that b number is negative, it's less than 0 to make this decay, the y-intercept, the starting initial value of this function, which I would get by plugging in 0 for x, it's going to be a times e to the 0, it's a times 1, it's just a. This is exactly what we observed in the previous video about exponential growth. So to solve for the half-life now, I could say, when will the output of the function equal half that a? When will it be half as big? So let's set up an equation that says half of a over 2, is equal to the function itself, a times e to the bx. And now we're going to solve for that value of x that will make this true. So let's see, I'm going to divide both sides by a, and so on the left I'm just going to get 1/2 equals e to the bx. I see an exponential base e, so I'm going to take a natural logarithm, and then I'm going to divide both sides by b, so I get x equals log of 1/2 all over b. That's a nice general formula that you can use for the half-life of an exponential decay function, or really the doubling time of an exponential growth function. It works for that too. The only difference is whether b is positive or negative. Let's use that to explore a particular exponential decay function based on a real-life situation where we know that the isotope carbon-14 has a particular half-life of 5,730 years or so. And this is how scientists estimate the age of a fossil, something that has organic material that has carbon in it, because we know how rapidly that isotope will decay over time. So if I know that this isotope has a half-life of about 5,730 years, then how long will it take for that original amount of carbon-14 in the fossil to decay to 50% of the original amount it had? Well, you know what? This is just another way of saying exactly what the half-life is. So in other words, my answer to this question, how old is the fossil, I can say it's pretty much the half-life. It's 5,730 years old. So that would suffice to just answer this question. I have another question or two coming up on the next slide, and I think it would be prudent and helpful right now to actually come up with a function that describes this scenario that we can use to better understand what's going on and then answer the questions that I have coming up. So let's establish a function. So I'm going to set up a function f of x that describes this scenario, and I'm going to say f of x is a function whose output is the proportion of the original amount of carbon-14 that remains after x years have passed. So in other words, what we know, what we're given, is that at time 0, after 0 years have passed, all of the original carbon-14 is remaining, all 100% of it. So I'm going to call the output 1 because I'm talking about this as a proportion. It's 100% of the original. And we also know that the half-life means that after 5,730 years, half of that amount is remaining. That's exactly what half-life means. Now let's look back to the previous slide where I solved for the half-life of a generic exponential decay function, and I found that it was this natural log of 1/2 all over b, where b is, again, that value that's the constant in the exponent part of the exponential decay function. So let's use that in our situation here. Since we know the half-life, and I know that that's equal to natural log of 1/2 over b, I can say let's set that equal to 5,730, the given half-life. And let's then solve for b, and that will allow me to set up an exponential decay function with specific numbers that describes this scenario. So I know that my function is supposed to be exponential decay, and it's going to be of the form a times e to the bx equals the function. And I know that b is this value, and that's coming from me rearranging this equation here. What about a? Well, in previous examples, we saw that a was exactly the initial value, which is 1. That's coming from the original value here. That's what's telling me a. So I can say that f of x is 1, or 100%, e to the, I'm just going to write bx, where b is this number here. And I'm going to skip to a new page to show you how to possibly simplify that, which may make it easier to interpret the function, and then we can decide which form of the function we're going to use to answer the questions coming up. So here's what I know. I have an exponential function, f of x equals e to the bx, and I know that b is the specific number, this log 1/2 divided by the half-life, 5,730. So let's show how to simplify this a little bit. If I write that like this, e to the if I write this as e to the b times x, and I've written out the value of b, but I've split that fraction, that division of log half divided by 5,730, I've written that as that numerator times 1 over the denominator. And the reason I'm doing that is that I'm about to apply an exponential property that we know that will make this look a little simpler. I can write this as e to the log of 1/2, and then all of that raised to the power x over 5,730. Why can I do that? Well, here is x over 5,730, that's going on here, and I'm really exploiting this property that says if I have, just use some other letters, x to the y, all of that raised to the z, that's x to the y times z. So I'm kind of using that property in reverse here. If I have a product in the exponent, like I do in that first version there on the left, I can write that as the base raised to the first factor, all of that raised to the second factor. And that's what I have going on the right over there. The reason for doing that is I can now exploit what we know about the inverse of exponential and logarithms to say that right there that I highlighted is really just 1/2. E to the log of 1/2 is just 1/2. This is another way to write the function. This is another form of the function. And I think this one might even help me better understand why the half-life of this function is 5,730. Think about it this way. If I plug in x equals 0, I get 1/2 to the 0, I get 1. So I can see f of 0 is 1. If I plug in 5,730, I'm going to get 1/2 to the, 5,730 divided by itself, I'm going to get 1/2 to the 1. I'm just going to get 1/2. If I plug in whatever double that half-life is, 11,460. If I plug in that, up here I'm going to divide by that first, so I'm going to see a 2, so I'm going to get 1/2 to the 2, I'm going to get 1/4. And that's what I've written out right there. So I can actually see that f of some multiple of the half-life is going to be 1/2 raised to whatever that multiple is. And so that means the output will have been cut in half exactly that many times. Now, I think that simplification, that rewriting of the function using that logarithm exponential property to get the base 1/2, I think that helps us better understand what the half-life means and why it's making the function decrease in that particular way. But to address the types of questions that I'm asking here, I think it'd be better to use the other form of the function because it's going to make the algebra, the solving of an equation, a little bit easier to write and do and calculate and crunch the numbers. So when I say, what if that had been 65% instead, I mean with the same setup, the same carbon-14 isotope with a half-life of 5,730 years. Let's say we dig up a fossil and it's determined that it has not half of the original amount that it started with, but it has 65% of the amount it started with. How old must the fossil be? Here's what I'm going to do. I'm going to set our exponential decay function, f of x, equal to 0.65, that's 65%. Remember that we set this up so that the function f outputs the proportion of the original amount of carbon-14 it had left. So when I say, what if it had been 65% of the original amount, that's asking what input will make the output equal 65%, or 0.65. So here I have set up an equation that represents the situation. I have our function f of x, which is e to the bx, and maybe now you can see why I've chosen to use that form of the function as opposed to this 1/2 raised to that power, because I think it'll be easier to solve. And in fact, I have pretty much all of it written out and done already here. By applying a natural logarithm on both sides, that allows me to simplify the left and treat the right as just some number. I would divide both sides by b here to get x equals natural log of 0.65, 65%, all divided by b. And now here is where I'm going to pull in what we know the value of b to be. I chose to write b as that constant right now just to make the writing of solving this equation easier. Now when I get to the crunch in the numbers step, I can actually plug in that value and see what this works out to be. And I calculate that to be around 3,561. And remember that x value is in years. So that's telling me that this fossil is around 3,560 years old, and it should make sense that that's, in fact, a little bit less than 5,730, because I'm asking when will the fossil have 65% of its amount left. So it's decaying from 100% down to 65%, so it hasn't decayed long enough to end up with only 50%, half. So it makes sense to me that this value is less than the half-life. It will take longer to decay down to 50%, and that's what I see from this. And that also should help me predict what's going to happen with my next question when I say, how long will it take to decay all the way down to 35% of the original amount? Well, I anticipate this answer to be a little bit larger than 5,730. And here I've set up and written out some of the steps for doing that, and setting the function equal to 0.35 for 35%, taking a natural log of both sides, dividing by b, and then here I've plugged in what we know the value of b is from previous work. I simplified a little bit on the next line, and then after crunching all those numbers, I find it to be around 8,678.5, so let's round up to 79. There's no reason to assume these are perfectly exact anyway, and that's years. This is the age of the fossil. And as I said, we predicted from the previous slide, this makes sense that this is longer than the half-life because it takes 5,730 years for the fossil to decay to half of its original amount, and it'll take a little bit more time to get all the way down to 35%, less than 50% of its original amount.